maybe it's the case for some of you. So today I will do an introduction about the land use statistic in Switzerland, so the base on what I'm working on, then a small introduction to the actual project, the ADEL project. I will not be long on that. If you have further question of the model itself, we can always chat afterwards. And then I will try to share this like small valuable pieces that I found useful in what I did. If you have questions along the way, don't hesitate to interrupt me. I just prefer to make just the first one and it's clear for you instead of going like to the end and you haven't got anything of what I was talking about. So the Federal Statistical Office of Switzerland generates many data. All the data are for free. There is more than what available on the website. So if you're interested in something very specific, get in touch with the people. You find like phone numbers, call the people, and yeah, don't hesitate to get the data from the OFS. So today we talk about the land use statistics in Switzerland. Land use statistics, it's composed by two different classifications. The land cover on one side with 27 classes and the land use with 46 classes. Here I just wrote some example of land use classes for residential area that you see the variety of the classes. So for example, for building, we have a small industry, big industry, residential area, terraced house, block top flats, public buildings, agricultural buildings, and unspecified buildings. So it's all different kind of buildings, and we'll try to detect that using aerial images. Okay, so you get a bit the challenge. The data set on which we work is composed by more than 4 million points that were surveyed already 4 times in the past, from around 1978, and now we are in the 5th survey. So we have people that, like this, that look at stereo images taken by airplanes that have many different information on the 3 screens, and for each of these 4 million points, they spend in average 12 seconds per point, and they give these 2 classifications to every point. Here is an example of statistics that you can create from such statistics here with only the changes that happened between 1985 and 2018 between aggregated classes. Okay, the automatization project is about accelerating the survey period. So before the survey period was around 9 years, and we tried to increase or decrease the time to 6 years so we can get more frequent statistics. Without the current project, there was already a part that was automatized or more filtered out, and with automatization we want to automatize more or less 2/3 of the whole work that is done by the interprets. The idea is that all the lands in the Alps where you find rocks, or the forest or agricultural land that usually don't change, they are not seen again. We filter them before the interpretation, so that people then can spend times working in urban areas where there is valuable work to do. Okay, here is a summary of the model. We use high resolution images. We try to use like elevation model, vegetation height models, infrared bands. There is a first CNN that extracts the information from the images, and then we mix that with register data, with cadastral data, so the official maps, with distance to roads, for example, distance to railways. And we have also a stack of satellite data of 20 years that we build from one year to another. It's the Landsat data stack. It's a bit of special thing that we have. And we mix all that in a second model to output 3 different things. So the probability of land use, the probability of land cover for every class, like the probability of a point to belong to a certain land use or land cover, and then the change probability as well. Okay, that was a bit fast maybe. If you have any question, can ask it now or later. Yes? Here? No, so we train it in a okay, the question is if it's a single model, we train it in a kind of sequential way by training different submodels. Yeah, actually, for the different data, like satellite data on the auxiliary data, we have some kind of submodels that are trained on that, where we try to extract the information, and then to build a kind of long vectors for final model that mix everything together. Okay, this is, I will not go more in detail now, but don't hesitate to write me if you have questions on that. Okay, that's a thing I built at home. Why? I have a pretty cool oven. It's an oven, a steamer, and a microwave. I think it's the first one in the world that exists. And the problem with my oven is that all the time I have these different plates because you cannot use, you need the glass plate for the microwave, and for the steamer you need another one. It was a burden to use because every time you change the function that you use, you have to go in the stack of the plates and then to try usually to take the last one because it's the one that you will not use, and to pop it out of the stack. Okay, you see the link with data here. So like that, I can just like, I have my plates that are sliced, and I can just take the plate I need. On the side, you see as well some metadata, how to use the plates. It's the instruction, and some other plates on the top that have another structure. Okay, we'll come back to that later. But I'm pretty proud of my craft. Okay, that here is a schema of how we build let's say the data pipeline at the beginning from the raw data. We're working with auto images from Swiss Topo up to the data that we use at the beginning of the machine learning algorithm. So we start with the raw GeoTIFF that are pretty big, then we start to cut them in GeoTIFF of 50 by 50 meters, and then to transfer them to Adrian, actually, we pack them in HDF5 packages because it was much easier to transfer them over the wire instead of like 4 millions of individual TIFFs. And then the HDF5 package needed to be transferred to PNG to be able to be ingested by the machine learning data pipe itself. And now we'll see how to do it better, because that was not usable in the administration environment. A big reason was actually the antivirus. If we had all the 4 million GeoTIFFs present on a disk and all the PNGs, the disk was just scanning all the time the images. That was the main issue, but not the only one. Okay, here an introduction to PyTorch data pipeline. Maybe you know that, maybe you don't. I think everything that you need to know is here. When you start to train a model, so first you start like the configuration, you set up your storage, your logging, etc. Then what you do is that you initialize a data pipe. So what is that? You're not reading all of your data because your data stack, usually it's too big, you cannot get it all in the RAM together. So you're preparing an object that is ready to send you the data while training. So what does it do? It starts different processes. So it spawns the Python process. And each of these processes will be ready to handle a slice of data. Okay, you see a bit the link with the plates now. When we train the model, the model like iterate along the batches, and it sends requests to the data pipe to get this new slice on data. And the data pipe like handle itself, and it asks individual processes to pre-process the data, so read them where it needs to be read, like do some modification before going to the ML pipeline if needed, and then send it back to do the actual training within the model. Okay, so how to do that smartly now? or smarter, or what was the best way we found to do it. So we did it this way. So first we built it a stack of HDF5 files. And in the pipeline, we just, at the beginning, in the initialization, we list all the files, we get the metadata, and we get some indices of every point that we want to load, okay? We shuffle them. Typically, like in an ML pipeline, you want to shuffle your data, because you don't want them in the same order all the time. So you have this like pre-process, like building of the indices. So you start by doing that. You just have the file list and then the indices, and you send that to your data pipe object for initialization. In the data pipe object, what we did is that in every process that we have, we opened all the HDF5 files. Every file contains here around 10,000 images, which makes files of around 2 to 3 gigabytes, which is quite nice to handle. For sending them to someone, or watching them in the Windows Explorer, or be scanned by the antivirus. So it's nice, just data package for us. And from here, what will happen is that we have all our files that are opened in every process. And then what's cool is that from the index we build here, we can directly target exactly which file we want to read by knowing where it is, like before reading it. We don't need to parse anything. Okay, seeing it with a snippet, so that's our data pipe object that is initialized with this index, it's the source data pipe and the file list, as I said. And we just, as I said, we just open all the files at the beginning of the iteration. And here we have the yield statement that handle the request from the training loop, and that just yield the image on the label and needed metadata, one at a time. And in the index, so the source data pipe that we iterate, we have the entry variable here. We see that we have the open files, and we read directly our stack, directly where we know where is the data that we need, that comes from the index at the beginning. It's really the idea of the plate. We know where every plate is. We don't have the plate yet, but we can just like blindly like open our files and just get the plate we need, like that. Okay, I believe you're excited by this, but it's not the end now, because this doesn't work very well if you do it exactly this way. And now there is the trick. Okay, that's small summary why HDF5 is amazing, and you don't need anything else. You can just build your format as you want. So anyway, small summary how you created your HDF5 files. Okay, because here is the trick that is nice to know. So you get some NumPy array, for example, like your data array from your function. You just open your HDF5 files, and then you write your data set this way. And what's important, actually, when you do this, is to specify the chunk size. The chunk size is that you will specify manually how the data are stored on the disk. Point. You made that yourself. On here, what we do is that we specify the chunk size as exactly fitting one image slice in our HDF5 files. And what will happen is that now, when our iter data pipe will iterate over the data, it will directly have a pointer in the HDF5 files where it reads the slice, and all the data are already like contiguous on the disk, and you will have like this data reader that works at lightning speed. So this was working on magnetic drive fantastically. So we were working with GPUs just with data like on chip drives. So that's, I think, valuable. For example, if you don't have SSD in your government agency, or just if you have let's say a cheap setup, if you don't have access to resources, to money, or if you want to do this kind of application with people that don't have your environment, that works really, really well. Okay, well, here it was just to say, okay, along with your image, what we do is that we store the metadata on the same way. We know exactly, like, all the time, like, where is our image located in the file, and at the same location we have the metadata, and we use the metadata actually to build the register at the beginning. So we iterate over all the files, we just get the metadata, we build our register, and then we can come and read the images that we need. And that makes our HDF file stack folder like that is well scanned by antivirus, that can be shared everywhere, that is nice to see on a corporate drive without 4 million PNG in it. And it just makes the job. It's a bit like the plates, it's a bit ugly, but it does what it needs to do. Yeah. Okay. Are there some questions until now? Still awake? Okay, another issue that we had was that I managed to get, like, I'm working on workstation for this project, like normal workstations. In some of them, I have the chance to have 2 GPUs, and on some others, there are 2 GPUs, but it's also used by someone else, and I want to, like, kind of use the workstation while someone else is doing some work on it without realizing that the performance goes down. So I have to, like, distribute the work in the department a bit like under the hood, let's say. And for that, I found, let's say, a trick or a way of organizing my work. It's just to use Optuna. Optuna is a hyperparameter framework. Maybe you know that. Maybe you don't. But yeah, the idea at the end, okay, or our conclusion is that we should not try to do complicated stuff with multiple computers and to try to distribute our work, like to use 2 GPUs for a single model handling using NCCL or whatever. That's just wasted resources in our environment. And the idea is just to use, like, we use the multi-computer for hyperparameterization. That is very valuable at the end of your project. And you just run like your different training on the different machines independently by using the Optuna storage to share the hyperparameterization. If people don't know exactly how Optuna is working, like, you have somewhere a database that is available. Usually everybody has that, either local or in any government you have access to a database. And then you can easily just set up this Optuna environment to do the read and write requests that are very light. There is just, that's what is shown here. There is just a simple read in the database at the beginning of your training and one write at the end of the training. So that doesn't overload the database, that doesn't overload the network, and it's very light solution. It breaks easily, meaning you can easily restart a training, and it's, I think, a very simple idea. But it's what I think the best way to use the computation power you have in your corporation. It's a very, very easy way to do it, at least. And since it's easy, then usually you kind of allowed to do it. Okay, the last idea that I want to share is self-tracking. So here I'm not talking about when. Okay, it's not about if you walked or not during the morning. It's not about what, meaning it's not about tracking the data you had on how you modify them, on having a copy of the data, but it's more about how you modified your data, on what you did, what you send as instruction to handle your data in when you're just working, for example, on GeoPandas, on manipulating the data. Sometimes you just don't record what you did, some buffering or stuff like that. And there is a simple way to record everything you did. So it's just by using IPython with a simple code snippet that you run just before opening the interactive shell, and that will just log all your commands on everything that you print. And actually, instead of working in a just standard Python shell, where you will have the history, but without the log of the print, you just open your shell like that, and that will just log everything you have. You remember the story at Twitter when Musk bought Twitter? He asked all the developers to print what they did in the last month, I think. There you can just hand in the output, where you would not have not any commit, and that's certainly useful. As well, I guess, if you work in banks or in government, when usually you have to prove what you have done, because you work for the public and not for yourself. Okay, just to finish the talk, here is just something more colorful, visual, an idea of a new product that we could build based on the model of the classification model we built to make a side product. But that's not a product yet. It's not planned to be a product yet, but it looks pretty nice, at least. Okay, so with that, I thank you a lot for your attention, and I hope you survived the trip with me. Thanks.
Thank you, Gillian. That was a very interesting talk, really. Are there questions from the audience? Yes, please. I'm going to walk around and give you the mic.
Yeah, thanks for the interesting talk. Could you go to one of your first slides?
The model, or?
The one where you showed the data loading?
The?
One more. No, go.
Go done? Okay. Tell me stop.
This one. Do I understand it correctly that the data processing is happening on the fly, basically?
Yes, the pre-processing is on the fly.
And okay, and then whatever is processed, you give it to the model, but is it somewhere written somewhere else?
No, we don't.
That means if you run the model tomorrow again, it will be crunching the data again?
Yes.
Why?
Why?
Why don't you write them somewhere? Because for energy, it's not really energy, time sufficient.
Typically, in your pre-processing, you have typically the data augmentation functions. You know, where you rotate a bit your data, you shrink it, etc. And you also have typically some different pre-processing functions. For example, very often the neural networks, they are a bit sensitive to the normalization of your data. And typically what I have, for example, is a hyperparameter for normalizing the data at the beginning. And for every different training that I have, I will try a different hyperparameter to normalize the data differently. So you have always usually some
Slight changes.
yeah, some things that change in the if it's not part of the ITER database, but there would also be some reason to do it. Yeah, our base data, for example, are images in like in bytes, 3 channels, 1 byte per channel. And as input of the model, we go with float 32. I think there are tensor float 32. So you save some storage space if you keep them in bytes. Different reasons.
You still have a question?
You can look for PyTorch, ITER, data pipe, or data pipeline. Pretty long documentation.
Hi, thanks for a nice talk. I was wondering, why did you pick HDF5, and did you consider other formats like NestEDF or ZAR?
No, we haven't done an extensive study on which format would be the best. I just stopped when I found what I needed. Yeah.
Okay, thanks.
I mean, it's really, when you start to work with HDI5, I mean, yesterday in the TileDB presentation, there was written like HDF5 is one of the very old formats known for 30 years. Like people like me that are pretty young, I don't know, maybe I'm pretty young, I didn't know this format before for very long. It's really convenient, and it's really the Swiss knife of format. So if you need something specific, like here, like for my ML setup, I really needed that, like this specific image stack of data that I can slice. You can do whatever you want with HDF5. So it's really, really cool. So